In this video, we're going to go over radioactive decay, okay? So what we're looking at here is we're looking at our different graphs. The first one, hopefully you recognize from GCSE. The second one, we're going to look at how do we do it if you can't easily divide by 2. And the last one is going to look at our NZ graph. And we'll figure out how can we calculate the activity if we've only got 1 gram of cobalt. So the first one is a really nice one. And sometimes they still do give you these really nice graphs where it's really easy for you to see what the half-life is. Because remember, half-life we represent now with T, that little subletter half. Half-life represents the time it takes to decay by half. The time it takes for the activity to drop by half, or the time it takes for the number of nuclei to drop by half. So let's say we've got activity measured in becquerels on my y-axis and my time on my x-axis. Clearly here, I can clearly find where 50 is, because there's 2, 4, 6, 8, 10. So then 50 is going to be right in the middle. The time it takes to drop by half from 100 down to 50. So I find that time it takes to drop by half. I can go across to my axes and down, and I can see what that time is. So here, for that half-life, I can see that time is roughly going to be around 12 seconds. So 12 seconds, okay? However, in this graph, when I've got number of nuclei against time, here we can see 100, but I can't just find where 50 is, go across and go down. Okay, so how do we do it here? How do we find the half-life? And the way to find the half-life here is t to the power of half is always equal to the natural log of 2 divided by the decay constant. And the decay constant there is the probability of decay. So you can't use the graph here. What we're going to do is you find out what the probability of decay is. Or there's another equation. We can say number of nuclei equals number of nuclei to begin with, e to the minus lambda times t. So what that means is we look at our number of nuclei at any time equals our n naught stands for the number of nuclei at the start. So here our number of nuclei at the start could be 100. And let's say I want to figure out what that decay constant is. So what I can do is e to the minus lambda, and I'm going to say, let's say we use a time of 20 seconds. So if I use a time of 20 seconds, my number of nuclei dropped to 80. So what I've got now is I'm going to write 80 equals 100 e to the minus lambda times t, and my time there was my 20 seconds. So you can see here, we can use this equation where we pick 2 points from our graph and the time it took to drop to that value to figure out what the decay constant is. Once we know what the decay constant is, we can insert it into this equation to find what the half-life is for that sample. Okay, so other things you might get asked to do is, let's say we know the initial activity. So again, there's that A naught. So that A naught stands for our initial activity, like N naught stands for the initial number of nuclei. Let's say we've got 512 becquerels. We know the half-life is given to this time is 10 years. We know what is the activity after 10 half-lives. Fun trick is, instead of you having to go 512 divided by 2 to get me 256, but let's just double check. So 512 divided by 2 to get me 256. That's 1 half-life, divide by 2 again, divide by 2 again, divide by 2 again. Trying to get to 10 half-lives. What we can do is you always do 0.5 to the power of the number of half-lives times that initial activity. So if it was 1 half-life, we do 0.5 to the power of 1 times by 512, and that's where you end up with that number, still 1 half-life of 256. So if I want 10 half-lives, we're going to do 0.5 to the power of 10 times by 512. So if we do that, 0.5 to the power of 10 multiplied by 512, we figure out after 10 half-lives, what I get left with is 0.5 becquerels. So barely anything left after our 10 half-lives. Okay, so 0.5 to the power 10 multiplied by 512. Next one is, so it might be a bit more likely, is again, if we've got cobalt 60, we're told what the half-life is, and I want to know what the activity is. Okay? The last equation I use quite often is how to calculate activity. And activity is always equal to the decay constant times the number of nuclei. Okay? So again, I'm not given the decay constant here, but I can see from this equation that to calculate the decay constant, I know that t to the power half, t in my half-life, is equal to the natural log of 2 divided by the decay constant. I know what the half-life is. It's 5.27 years. Okay, so 5.27 years. You can keep it in years if you want, but normally activity is measured in becquerels, so power of seconds. So I'd highly recommend you convert that into seconds because it just makes your life easier. So we multiply by 365 to get it into days, multiply by 24 to get it in hours, multiply by 60 to get it in minutes, and multiply by 60 to get it into seconds. So if I do 5.27 multiplied by 365, multiplied by 24, multiplied by 60, multiplied by 60, we can figure out there that the half-life in seconds is equal to 166194720. But I'd highly recommend just keeping that number in your calculator rather than copying it out. So to find what the to find what the decay constant is, which is do natural log of 2 divided by that previous answer. So we just do the natural log of 2 in your calculator and you're dividing it by your previous answer. So we get our decay constant then comes out with 4.17 times 10 to the negative 9 becquerels, or seconds to the minus 1. Okay, so now I have the decay constant, I can find out what my activity is. So my activity is equal to that decay constant times the number of nuclei. Hopefully you're thinking here, I don't have the number of nuclei, I have the mass. So that's when you have to use your two new equations, your two equations from GCSEs to figure out how do we get from a mass into a number of nuclei. And this one's not on your formula sheet, you need to remember it. And this is when hopefully you're thinking to get a mass, a number of nuclei, we do number of moles is always equal to the mass divided by the relative molecular mass. So to calculate the number of moles, I do my mass, and because it's a chemistry equation, we have to keep it in grams. Divided by the relative molecular mass, it's cobalt 60. So the relative molecular mass there is 60. So I calculate the number of moles. But again, that's not my number of nuclei. And that's our other equation, remember. The number of nuclei is always equal to the number of moles times by Avogadro's constant. And Avogadro's constant is on your data sheet. And that number is 6.02 times 10 to the power 23. So to calculate the number of nuclei then, I have to do 1 over 60, my number of moles, multiplied by that Avogadro's constant to get my number of nuclei is. So we do 6.02 times 10 to the power 23, and we multiply by 1 over 60. To figure out the number of nuclei we have is 1.0 times 10 to the power 22. So then for our final answer, to get our activity now, all we have to do is that we're going to take our decay constant, 4.17 times 10 to the negative 9, multiplied by our number of nuclei, which is 1 times 10 to the power 22, to figure out what our activity is. So again, we're doing 4.17 times 10 to the power negative 9, multiplied by 1 times 10 to the power 22, and we get an activity there of 4.17 times 10 to the power of 13 becquerels. Grand. Okay, last thing on our picture here is we're looking at our NZ graph. Okay, so N, remember, stands for the number of neutrons, and Z stands for the number of protons. Okay, so for really light nuclei, what's going to happen is, so light nuclei less than the mass number of 20, for light nuclei, the number of neutrons always equals the number of protons, so roughly up to 20. So there's 20 protons, there's going to be 20 neutrons. When we get to heavier nuclei, what happens is you want to have slightly more neutrons inside your nucleus than protons. So we call this the stability line. So we can see here that our stability line slightly sways up to the number of neutrons side. So what we're saying here is, say we've got a heavier nucleus like 90 protons. If I go up, instead of having my 90 neutrons, what we actually have, we're going to have more. We might have something like 150 neutrons. So hopefully you're thinking, why would you want more neutrons in a nucleus than protons? And we know that in a nucleus, when you have protons and neutrons, you want to have more neutrons because remember, those protons want to repel each other. They want to split that nucleus up. So the protons want to repel each other because that electrostatic force of repulsion. But to keep it all together, what we have is this strong nuclear force. So again, the strong nuclear force is trying to bring that all together. So we're going to think now, what happens, what type of decay happens at these different regions of the graph. Okay, so if you look at an earlier video when we did stable and unstable nuclei, we looked at alpha, beta, and gamma radiation and gamma decay in a bit more detail. But just as a quick overview here, remember what we said was, if we have any nuclei that fall towards the left of that stability line. So if I have some nuclei that falls to the left of my stability line, so here, clearly we can see that they have, if we go up, they have too many neutrons, right? They're on this side. They're supposed to have that many neutrons, but they've got too many neutrons. So here, if we've got too many neutrons, trying to think what type of decay is going to happen. And if someone's got too many neutrons and we want to get rid of that neutron, we know that the thing that's going to happen is my neutron can decay into my proton. My neutron decays my proton, and then to conserve charge, we're going to get our electron emitted. That's why it's our beta minus decay. And then to conserve our lepton number, we know we're also going to have a neutrino, but it's going to be the antiparticle emitted. So again, look at our earlier video if you want to figure out how to calculate the conservation there, the conservation of the baryon number and the lepton number if you can't remember how to do that. So again, if there's too many neutrons, we know it's going to do beta minus decay. If it's towards the right of that stability line, so let's say it falls, whoop, I've got too many pens here. Let's say it falls somewhere here. So again, if I go up to see what's happening, again, I can see what's happening here is it's got too many protons. So the problem here is there's too many protons because look, it's supposed to have, if it's got that many neutrons, it's supposed to have that number of protons, but it's got too many. So again, we have to think what type of decay happens if we've got too many protons. And hopefully you're thinking if I've got too many protons, what happens is one of my protons is going to change into my neutron. It's going to decay to my neutron. And to conserve charge, we know we're going to have a positron, and to conserve lepton number, we're going to have our neutrino emitted. So again, because it's a positron emitted, we know there's too many protons, that's going to be a beta positive decay. And the last part of the graph that you need to know what type of decay occurs is when we have a really high nucleon number. So if you have a high nucleon number, like above 60, that's always going to be your alpha decay, because it wants to get rid of both protons and neutrons.